Okay, so this is our first problem in section 7.4. We have 6 pieces to play at a recital. So let's just call the pieces, I don't know, just to make life easy, let's call them A, B, C, D, E, and F. Okay, those are the 6 pieces we want to play. Now, how many ways, so let's sort of think about the program that she's going to have. Okay, so she's going to have her first piece that she plays, right? Then she's going to have her second, etc. She has to arrange these into slots. And so what can she choose to put in the first slot? Well, any of them, right? So how many different choices does she have for that first position? 6 choices. Okay, so it doesn't matter which one she picks, but let's say she picks piece E, right? I'd pick piece E because E looks like the most pleasant piano piece, doesn't it? I mean, A sounds like it's like kind of too full of itself. Hey, I'm A, you know? I don't know. E just sounds kind of fun, right? So I'd put E first. No, I'm just being silly. But anyway, so I'd put, so let's just say she puts E first. Now, she's not replacing the item. It's gone. That's called without replacement. Without replacement means once you choose something, it's gone, right? C'est la vie, as they say in French, right? Okay, so it's gone. So now how many pieces does she have left for the second item in the program? 5 pieces. And now let's say she picks, I don't know, choice B. It's gone. Okay, so how many pieces are left for the next one? 4. Let's say she picks choice A. There's 3 left for the next one, 3 choices. Doesn't matter which one she picks. How many are left for the next one? 2. And then how many are left for the last one? 1. Okay, so in other words, we're reducing the number of choices by 1 each time because we're sampling or choosing without replacement. So the number of items available goes down by 1 each time. Okay? If we were replacing, then it would just be 6 every time. And you could play the same piece over again. In theory, you could, you know, it'd be a rare event, but if we were replacing the choice, you could in theory just play the same piece 6 times in a row. Okay, which would kind of be silly. That's why this is a without replacement scenario. Okay? Now, of course, when we multiply a number by all the numbers before it, we can simplify that to factorial, right? So I can write this number as 6 factorial, which you can easily do on your calculator. Okay? So a simple factorial, when is a simple factorial like this going to be the result? It's going to be the result when we are choosing, you know, n items out of n. In other words, in this case, we're choosing 6 songs or pieces out of 6. In other words, we're choosing all of them, but without replacement. Okay, that's the key. Now, what if I wasn't choosing 6 pieces out of 6? What if she was only choosing like 3 pieces? Then it would just be 6 times 5 times 4. So it wouldn't quite be a factorial. It wouldn't be 6 factorial anymore. It would be a slightly more complicated expression. Okay? So in fact, let's just kind of analyze that just as a little bit of extra practice. So let's say, so as an extra example, let's say she chooses 3 items out of the 6. So she chooses 3 pieces out of the 6. Out of the 6. Okay, so there's 6 available. Let's say she chooses 3 of them. So here's the first slot, second slot, third slot, right? Piece number 1, piece number 2, piece number 3. How many ways can she choose piece number 1? 6 ways. How many can she choose? How many ways for piece number 2? 5 ways because we're sampling without replacement, right? 4 ways for the third piece in the recital. And so the number of ways, if she was going to choose 3 pieces out of the 6, okay, then it's just 6 times 5 times 4 ways. Now, can we write that in factorial form? Well, yeah, we could do 6 factorial, but 6 factorial is really what? 6, 5, 4, 3, 2, 1. Again, this is just an extra example that we're doing here, so let's just not confuse that with the main example. Okay, but I need, the problem is I don't want the 3, 2, 1, so I have to get rid of it. And the way to get rid of it is to divide out the 3 times 2 times 1, because that'll cancel it out. So that means I'm going to divide by 3 factorial. that removes the 3. There would be sort of a, times 3 times 2 times 1. I don't want that, so I'm going to get rid of it by dividing. Okay, so I'm taking 6 factorial divided by 3 factorial. Okay, now, do you guys recognize that? Okay, you should recognize that as a permutations, right? So if you go to the permutations formula, I'm kind of running out of room here, but I'll kind of squeeze it in up here. So 6p3 would be 6 pieces chosen. Well, you basically have 6 pieces to choose from. You're picking 3 of them. Okay, and permutations means the order matters. P equals permutations. Okay, I'll just write permute, which means the order matters. Or permute means order, or change the order. So the order matters. Right, if you look up the word permute in the dictionary, okay, it means move the order around. Okay, so the order matters, and also obviously without replacement. If you're doing replacement, then it's just 6 times 6 times 6 times 6 times 6 times 6. Right, there's 6 ways to choose each of them. So without replacement is where things get more complicated. That's where the number of items changes each time, and that's why we have complicated formulas. So in essence. We could, if we were choosing 3 of the 6, it's a permutation, 6 things chosen 3 at a time. And so what would be the formula for that? That would be 6 factorial over 6 minus 3 factorial, right, which is what we have here. Okay, that's 6 factorial over 3 factorial. Okay. So to take this discussion a little further, if you look at the initial problem, here's the original problem, right? Here's the original solution for the original problem. You could think of that if you want as, I can think of this situation, which is, this is the sort of the scenario, and then our analysis of it, our resulting formula was here. We could think of that as 6p6, if you like. We have 6 pieces, 6 piano pieces to choose from, and we're choosing all 6 of them. Okay, order matters. Order matters means permutations. Now, what would be the formula for 6p6? It would be, remember, the formula for NPN, if you look it up in the formula sheet, is, n choose r, my bad, okay, is n factorial over n minus r factorial. Okay, so 6p6 would be 6 factorial over 6 minus 6 factorial, which is 6 factorial over 0 factorial, and 0 factorial is defined to be 1. So it's just 6 factorial over 1, which is just 6 factorial. So you get the correct answer. Okay, now you don't need to think of it if you're choosing all items that are available, like all 6, there's 6 things to choose from, and we're choosing all 6 of them, order matters, no replacement. Then it's just 6, 5, 4, 3, 2, 1. It's just 6 factorial. You don't need to think of it as a permutation, but if you did, the permutation formula still works. Okay? So when do you use permutations? When permutations and combinations, the complicated formulas, and even factorials, only occur when there's no replacement, without replacement. If there's replacement, if she could choose, like if we're choosing a piece and then she throws it back into the selection process again, so she might choose it again, then it's just 6 choices times 6 choices times 6 choices times 6 times 6 times 6. Okay? So it'd be 6 to the power 6 in this case. But if there's without replacement, then we have the numbers going down each time, and then we have issues with factorials and permutations and combinations. If the order matters, then it's permutations. If the order doesn't matter, it's combinations. Okay? So in this case, the order matters because playing the pieces in the recital in one order is different than playing them in a different order. Okay? Anyway, so we kind of went above and beyond the question here, but that's okay because we're trying to master the concept. All right, so let's go on to the next question. Okay, so now we're on problem number 2. And so we're selecting meals at a restaurant. So we can choose an appetizer. Then we can choose a soup or salad. So you have your choice. You can't have both unless you want to pay extra. So which one do you get? Well, it depends what the soup is. Okay. And then if the soup's good, forget the salad, right? But anyway, then we have entree. and then we've got the dessert. Okay. So, how many ways can we choose an appetizer? There's 7 appetizers. Now, are we sort of choosing an appetizer and then either replacing or not replacing that appetizer and choosing another one and then another one? No, we just have 7 appetizers. There's no either replacement or non-replacement here. There's just 7 items to choose from. Okay. What about soup or salad? Well, there's 3 salads, 3 soups. Think of this as just 6 items you can choose from. How about the entree? How about the dessert? Okay. Now, if there are 7 ways to choose the first item, then 6 ways to choose the second, 13 ways to choose the third item, 2 ways to choose the fourth item, then how many ways are there to choose any combination, any particular sort of string of these things? And the answer is we just multiply. Okay, and that's your answer. We already have the answer on the screen, right? We just multiply these out and we get some ginormous number. Okay, let me see what I get here. I'll grab my calculator. I'm getting 7 times 6 times 13 times 2, 1,092 ways to choose a meal for this particular restaurant. Now compare that to the previous example. The previous example, if you recall, was the piano recital. In the piano recital, you had item number 1, item number 2, item number 3, item 4, item 5, item 6. This is the piano recital. And how many ways were there to choose the different items? Well, there were 6 ways. Then we are not replacing. And we're choosing from the same pool of items, but we're not replacing the item. So the items go down to 5. Then we're choosing from the same pool of items, not replacing. Same pool of items, not replacing. Same pool of items, same pool of items. In this case, these are different pools of items. The appetizers are different than the soup salads. Those are different than the entrees, and those are different than the desserts. Choosing an entree does not alter the number of things available, let's say, for the desserts. They don't influence each other. They're 4 separate categories. So in the piano recital, if you think about it, we were choosing 6 things all from the same category. Choosing 6 items all from the same category. Right. In the case of the meals, right, in the meals example, we've got these are all different categories. We have 4 different categories. We have 4 slots that we have to fill in. Each is a different category. So each one is its own number. So each is a separate category. It's not the same category. Okay? If I was choosing like 7 different appetizers all from the same appetizer category, it would be 7 times 6 times 5 times 4, etc. Okay? Because I would keep reducing by 1. All right. So you guys see the difference between different categories. You just multiply the number of choices in each category. If it's the same category, it gets more complicated because you're altering the category when you make each choice. Okay? All right. So let's go on. Okay, so here we are on problem number 3. So on problem 3, we are testing 5 different brands of soft drinks. So just for sake of argument, let's just call them A, B, C, D, and E, okay, for just our different brands. Now, we're trying to select pairs. Okay, so what does a pair look like? First choice, right, you have a first item in the pair, second item in the pair, item 1, item 2. Now, how many ways are there to choose the first item? Well, looks like there's 5 different ways, right? Now, can I pair an item with itself? Well, that doesn't make sense, does it? That means I'm sampling with what? With replacement or without? If I can pair it with itself, like if I could choose brand A and pair it with brand A, that means A is back in the pool of drinks, which means I was replacing it. That is silly. We're not going to pair something with itself. So we're going to sample without replacement. Okay, so when we're not replacing, that means we're in the world of factorials. We're in the world of factorials and permutations and combinations, right? We're not in the world of simply just, I mean, if it was just, if I was replacing, it would just be 5 choices for the first guy, 5 choices for the second guy, and I'm done. There'd be 25 ways to do things, okay? But because I'm not replacing, without replacement, then things get more complicated. So how many ways are there? So as soon as I choose a soft drink, how many ways are there to choose the second soft drink? 4 ways, right? Okay. Now, if I go ahead and, can I write this in factorial form? Well, yeah, I could write 5 factorial, but wait a minute. 5 factorial is really what? 5 times 4 times 3 times 2 times 1. Is that what I have here? No, I just have 5 times 4. I don't want the 3, 2, 1. So how do I get rid of the 3, 2, 1? You get rid of it by dividing by it. How do you divide by it? So I'm dividing by 3, 2, 1 to cancel it off. The way I do that is I divide by 3 factorial. The 3 factorial on the bottom is really 3, 2, 1, and that will cancel the 3 times 2 times 1 on the top. Okay, now do you guys recognize this? This is what? This is permutations or combinations. This is permutations. This is permutations, 5 items, and we're choosing them, what? 2 at a time, right? The formula for 5 permute 2 would be what? 5 factorial over 5 minus 2 factorial. Okay, which is 5 factorial over 3 factorial, which is what we have here. But wait a minute. We have an issue. And the issue is, does the order of how we choose things matter? In other words, let's say I choose soft drink A first, and then I choose soft drink B. That means my pair would be AB, right? A and B. But what if I chose B first and then A? Is that the same pair? In this case, it is. Now, if we were talking about like piano recital programs, then that's different, right? Playing piano choice A and then choice B is different than doing B then A. So in piano recitals, the order did matter. But in choosing pairs of soft drinks to pair with each other, the order does not matter. Okay, so the analysis I have right now, this analysis that we see on the screen right here, would be correct if the order is what? If the order matters. Okay, this is if the order matters. If the order is important. Okay, if the order matters, there's going to be 5 times 4, which is 20 possible pairs. Okay, so, but we actually have the order not mattering. In fact, if you want to be all fancy about this, a little crazy here, but I could actually write down all 20 combos. You ready? Or actually all 20 permutations. You ready? Here they are. I could do A with B. I could do A with C. I could do A with D. I could do A with E. I could do B with C, B with D, B with E. Okay, I could do C with D, C with E, and I could do D with E. Whoops, I'm running out of room there, but D with E. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 of them. Now, if the order matters, that would mean that choosing B first and then A first would be a different selection if the order matters. Okay, so choose A first for your first soft drink, then choose B would be different than choosing B first and then A, if the order matters. Now, in reality, the order doesn't matter here, but I'm just trying to kind of show you what's happening, how we construct the answer. So if the order mattered, A then B is different than B then A. AC would be different than CA. AD would be different than DA, etc. I can just reverse all of these, and I get a different selection if the order mattered. Okay, what I'm claiming is that the order really doesn't matter, but let's kind of go through the argument here and just to understand a little better what's happening. Okay, so here's my 20 combos. Okay, well, actually I should say 20 permutations. We in everyday language we call them combinations. Anytime you put something with something else in everyday language, you call it a combination. But in probability world, combinations and permutations mean different things. If the order matters, they're called permutations. So here's my 20 permutations. I've got 10 and another 10. Now in reality, these guys are the same in terms of pairing soft drinks. These guys are the same. these guys are the same as each other, etc. We can go all the way down the list. Each of these pairs, each of these possible permutations is the same as the other one across from it, right? These are all kind of the same combination of soft drinks. How many different categories of the, like A, B, and BA, that's one possible pairing. How many pairings are there? There's 10 of them. So how do I reduce the 20, which is what I have here, 5 times 4, right? There were 5 ways to do this, 4 ways to do this. That's 20. How do I reduce it to 10? The answer is divide by 2. Okay, now where's the 2 coming from? The 2 is coming from the fact that there's 2 at a time that are considered the same as each other. I'm taking 2 different permutations and considering them one combo. A with B in either order, AB or BA is a combo. That combo is the same no matter how you write it. If you write A first then B or B first then A, it's the same combo. Okay, it's just the AB combo. This is the AC combo. This is the AD combo, etc. Okay, so remember the formula for combinations, or actually the formula for permutations, which is what we have here. The formula for permutations, so if the order matters, that's permutations, P. Okay, permutations. And the formula for permutations is NPR is n factorial over n minus r factorial. That's what we did here, right? 5 factorial over 5 minus 2 factorial. Now, if I want to group things together, I'm going to reduce the number of items by 2. Okay, so if the order does not matter, so let's kind of change colors here. So now if the order does not matter, okay, what's going to happen? If the order does not matter, then I'm going to have combinations, NCR. And what's the formula for NCR? N factorial over n minus r factorial, just like before, but now we're also going to divide by r factorial. That r factorial says I'm going to take each of my, in this case, two permutations and pair them together so that they represent one combination. That's what this is doing. It's reducing, when you add that extra factor on the bottom in the denominator, you're reducing the result. You're making the result smaller because you're grouping things together. When order does not matter, your things that used to be counted as different items, AB used to be counted as different from BA, you're grouping them together now and counting them as one item. Okay? So in my case, I'm going to have, I've got 5 soft drinks, and I'm combining them 2 at a time. C is because the order does not matter. Okay? So that's going to be 5 factorial. Whoops, my pen is kind of acting funny. Over 5 minus 2 factorial, which is what we had before, right? That's what we had up here. But now I'm going to divide by an extra 2, technically 2 factorial, which is just 2, because 2 times 1 is just 2. Okay, because I'm pairing together, each time I have like AB versus BA, they're getting grouped together to one thing. That's what this is doing. Okay, and I can compute that, and I'm just going to get 10. In this case, 10 ways for this to happen. Okay, which makes sense. Here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if order does not matter, it's combos. Combos has the extra factor of r factorial on the bottom to reduce or group together different permutations that used to be counted as different things are now counted together. And this does that for you. That extra r factorial factor on the bottom is the grouping factor. That's the grouping factor, group stuff together. Okay? And so my result here is 10. All right, cool. So this is the actual, so if for some reason the order mattered, then we would be doing permutations and we'd have 20. But if the order doesn't matter, it's the permutations divided by 2 factorial, and so that's combinations, and that's 10 in this case. All right, cool. Okay, so let's just skip ahead briefly to number 6, because it's a good comparison to what we just did before. So on number 6, I've got to create a 3-digit code. Okay, so I can have my first digit, I'll call it digit 1. My second digit is going to go in this box. I'll call it digit 2. My third digit will go in this box. We'll call it digit 3. Okay, 3 digits. Now, how many choices can I make for my first digit? Well, how many different numbers are there? 0 through 9 is actually 10 items, right? There's 10 choices here because the 0 is my first choice. So how many choices do I have for my first digit? 10 choices. Now, does that reduce, first of all, am I choosing from the same pool of items? Like think about the piano recital, same pool of items, or am I choosing from different pools of items, like in the different meals at the restaurant? Like the entree category is separate from the dessert category, that sort of thing. Well, in this case, I'm choosing from the same pool of items, the digits, okay, but we are allowed to repeat. That means with replacement. So for example, if I choose like the digit, 7 as my first choice, I can choose that again. I'm replacing it, okay? So when you're choosing with replacement, we don't need factorials, we don't need combinations, we don't need permutations. We just count, okay? There's 10 choices for the first digit. Can I choose anything again for the second digit? Yes. Like if you want to make a combo that's just 777, can you do it? Is that legal? In the state of Arizona, that is, right? 777 is legal in the state of Arizona, right? Good thing we're not in New Mexico. Well, no, I'm just kidding. Okay. Digit 2, you can choose 10 different ways. How about digit 3? 10 different ways. Done. Problem's over. Okay? When you're sampling with replacement, it's just number of ways the event can be chosen. Okay? Times the number of ways the event can be chosen, times the number of ways the event can be chosen. What about the restaurant scenario? In the restaurant scenario, you had entrees, you had what was it? Appetizer, soup salad, entree, and dessert, and you just were straight multiplying across. How come? Because we weren't sampling without replacement. We were simply just choosing from different categories, but we were not reducing the number of items available in the category after each choice. The only time things get complicated is when you're reducing the number of things available after each choice. Then you start to get complicated formulas. Okay? All right, cool.